This week we're looking at pressure measurements, and the assignment is going to be about measuring pressure transients. One of the common places where we need to know what's going on in pressure is the pressure inside the cylinder of an internal combustion engine, like a diesel engine. And knowing that pressure is really critical to pollution production, and that's a really important engineering and ethical issue. So you can follow this link in the notebook to find out some more about what's going on. Now, what I've done here is I've pulled out a paper that some people in Austria have written on measurements that they've been making in diesel engines, pressure measurements inside the cylinder, and they're making these measurements particularly to estimate the amount of oxides of nitrogen produced by these engines. And that's a critical element for meeting emission requirements. Now, these are the kinds of results they've been getting. On their test bench, they've been using some research engines and controlling things fairly tightly. And in all four cylinders of the engine, they're using Kistler brand. Kistler is a transducer manufacturer, indicated pressure measurement sensors. So this is the kind of information that they're getting out in terms of pressure traces. As the piston comes up to top dead center, we get full compression, we get a compression ignition. In a diesel engine, the pressure rises and then it comes back down again to a lower level. So this is the pressure that's doing all of the work in a diesel engine. Now, if we look at some particular pressure traces here you can see a pressure trace which is almost symmetric. That's where the engine's under very low load. It's compressing the air, and then the air is pushing the piston back down again. Over here, we're at a much higher load where the air is being compressed, fuel is injected, and then there's significant combustion. The pressure goes up substantially, and that increase in pressure is what provides the extra power driving on the downstroke of the piston. So to understand what's going on, we'd like to be able to measure this pressure variation as a function of time to be able to know what's going on in the engine. So that's the background idea, and the paper is in the zip file. You can have a look at the details in the paper if you like, but we're going to concentrate just on the pressure traces and would we be able to measure them. So let's start off by doing the usual things. We're going to import the libraries that we already typically are importing, and we're going to import this exponential smoothing function that we developed before as well. We'll approximate a high power pressure trace analytically. Now, looking up here at this shape here, I noticed that, well, in general, it sort of went up and back down again, so that's sort of a Gaussian shape, at least in its geometry. And it had another little peak there from the compression before the fuel was injected, and a much stronger peak over here after the fuel was injected. So I'm going to try to generate something that looks like that shape. I won't worry about the physics. I'm going to just worry about getting the shape to look about the same. So what I've done here is I've defined this function called pressure trace, and it takes a variety of inputs. Most of them have default settings, and I played with these default numbers to get a fairly sensible sort of a shape. And what we do is we pass to it a crank angle in degrees, and it will figure out what the pressure trace ought to look like for that array of crank angles in degrees. So I'm going to figure out what the halfway point is here. This is halfway along the crank angle range, and that should be the middle of the pressure transient. First I'll set the whole region to a normalized PDF, a Gaussian distribution that's spread over the whole zone, and then I'll add a peak before top dead center, so with a mean of P1, and I'll add another peak after top dead center with a mean of P2. So in this case, I've set P1 equal to minus 7 degrees and P2 equal to plus 11 degrees. And I played with these parameters just to get the shape I wanted. So let's run this code and see what comes out. I get a pressure trace that looks like this. It's got the same general characteristics. It starts low, goes up, has a little bit of a peak here, and then as the fuel is injected, it's got a large rise in pressure and comes back down again. So I'm getting the kind of result I'd like to. It's got about the same shape. I can use this as a test to see if I could measure that shape with my pressure transducers. So the way I created that was I said, let's take crank angles that go from negative 100 to 100 degrees, and let's take 1,000 of them. So that was just back up here. I noticed that their traces were going from negative 100 to 100, so I wanted to look at the same region. I took 1,000 points so that I would have enough points to get a reasonably smooth curve. I then went and called the pressure trace function, and it created these 3 different elements to contribute to that pressure trace and make the shape. I found the time that corresponded to the crank angle in degrees. Well, degrees divided by 360 is going to be position in rotation. And if I have 1,000 RPM, then that would be 1,000 revolutions per minute. Or the time it takes to make 1 revolution, if we wanted it in seconds, would be 60 seconds per 1,000 revolutions. Or if I was operating at 3,000 RPM, I'd calculate that with a 3,000 in the denominator there. So I can calculate the time as well, and I could plot either versus crank angle or versus time. I've increased the pressure by a factor of 200 because this trace is providing me with a normalized output. It's normalizing the results to 1. So I want the maximum pressure to be about 200 bar because that's a reasonable sort of a number for a diesel engine. So I'm just generating some fake data here to do my simulations on. And if I run that again, let's plot it versus time instead of versus crank angle. And I see exactly the same shape, but now I see that this is all happening really quickly. I've got 0 time, that's top dead center. There's 2 milliseconds after top dead center. There's 2 milliseconds before top dead center. This is all happening very quickly if we're operating at 3,000 RPM. So I'm going to need a really fast pressure sensor. And that means I'm going to have to worry about the transient response of my pressure sensor. So if I've got a pressure transducer, we've seen an example showing how a pressure transducer might follow a second order response. And we've done this second order response before for the cantilever beam load cell. We didn't know K and C or how to calculate them, but we remember from our ODEs course that the natural frequency will be about the square root of K, and that's in radians per second, or it'll be the square root of K divided by 2 pi if we want to put it in hertz. And usually, if we're sourcing pressure transducers, at least good quality transducers, we should be able to find that natural frequency from the manufacturer's data sheet. And there's a Kistler data sheet actually attached to this package for an in-cylinder pressure transducer that says it has a natural frequency greater than 65 kilohertz, 65,000 hertz. Now, by observation, I found that setting the damping factor equal to the natural frequency in hertz causes the oscillations to damp out in about 10 cycles, whatever the natural frequency. So that seems like a good guess if we lack other information about the damping factor. We'd need to know a lot about the construction of these transducers if we wanted to know about their damping performance. So lacking that other information, we can go through and have a function calculate the second order response from the inputs. So let's start by making sure it works for square waves. So I'm defining this square wave input here, and this is just instead of the pressure trace, it's producing a square wave result. And then I've got this function y measured, and it's going to return the measured response from my pressure transducer or any second order measurement device based on the time scale, the actual value that I'm trying to follow with my transducer rather than the measured value, the two coefficients that go into the ordinary differential equation that governs the response, and another flag that tells us whether we want to plot. Now this code here is doing exactly the same thing that we did in the previous assignments to monitor second order response. So it's getting the time step, it's setting up space to calculate the measured value, the derivative, and the second derivative. It's setting the initial conditions, and then it's going through and actually calculating those derivatives as a function of time and plotting them out. So what I'm going to do is I'm going to create a space in time that goes over a relatively short range, and then I'm going to populate it with a square wave. And I'll multiply it by 200 to get me into the same pressure range as I was working with. And I'll set the natural frequency of my pressure transducer to 65,000, like the natural frequency of the Kistler transducer that we're using as a model. I can calculate the natural frequency in radians per second just by multiplying by 2 pi, and I can put that in the square of that as my k value for my prediction of the measurement. And finally, lacking anything better to put in for a damping factor, I'm just going to put in the frequency in hertz and see what comes out. So I'm going to comment out this segment for the moment, and let's run that code. So what this has done is it shows you that the square wave trace is going up and down like this, and in orange we can see the transducer trying to follow it, and it's got a fair bit of oscillation on it. So let's zoom in and see one of those traces. So I've just zoomed the X scale, and we can see that here's the actual pressure transient, our square wave that we're trying to approximate, and here's our second order response going down and up and down and up and damping out after about 10 oscillations. And that's typically what we'd expect to see, is some damping like that on our second order system. And it repeats going up and going down. It'll run as many times as we give it transients. Now let's check this 65,000 hertz. Well, this time from here, that's 2 milliseconds, that's 2.2 milliseconds, so that's 1/10,000th of a second in there. And it seems to be oscillating up and down about 6.5 times. So yeah, I do think I'm getting a 65,000 hertz natural frequency from the response of the pressure transducer. So I've run it with a square wave, and it checks out. So that's good. So now the question is, how well does this Kistler transducer follow our pressure transient? And Kistler specifies a natural frequency greater than 65 kilohertz. So let's assume our natural frequency is 65 kilohertz. We'd like to put in a space for the crank angle, and this time I'm going to resolve it over a lot of 100,000 different steps, just to make sure that I don't blow up my simulation. I'll get D and P from my pressure trace function that I used before. I'll get the time by looking at it as if it's 3,000 RPM. So that's the fraction through the rotations, crank angle degrees divided by 360 times 60 seconds per 3,000 revolutions. And I'll up the pressure to 200 bar just to get it on the right sort of scale. And now I'll look at the response that I get. So let's run that. And it runs reasonably quickly at 100,000 steps. And the result I get is not too bad. It looks like the orange and the blue are pretty much right on top of each other in this picture here. So it looks like I'm following quite closely. Now let's just see what happens if I try to do my simulation a little faster over fewer points. It comes apart and explodes. I've got 1 times 10 to the 269 there. So my calculation became unstable. So let's make sure that we have at least 100,000. Let's go up to 1,000,000 and see what happens. If we run it with 1,000,000 samples, it'll take quite a bit longer to do the calculation, but we still get the same result. So I think we can go back to 100,000 as a reasonable simulation time. And let's see what happens if we used a slower transducer. Well, let's try 10,000 instead. 10,000 is still good. Let's try 100. I don't think 100 is giving me the right answer. So if our natural frequency for our pressure transducer is 100 hertz and it doesn't have very much damping, then we're going to see that it's starting to ring because of the oscillations in this single pressure transient. It can't follow the transient, and it can't damp out fast enough before the next transient comes along. What if it had more damping? Let's increase the damping and see what happens. Well, it's rising and falling more slowly, but it looks like it might get back down to where it's going. It didn't have as high an altitude there. But I think this pressure transducer would be just too slow. So far, I'm convinced that this Kistler pressure transducer with a natural frequency of about 65,000 is entirely adequate to follow this pressure transient at 3,000 RPM and give us good, accurate representations. So I've reassured myself that up here in the paper, when they chose Kistler transducers, that they were actually able to properly resolve the appropriate pressure. The only problem is Kistler transducers are really expensive because they've got such a high frequency response. And if we were doing research, that's usually not a problem. But if we want to put one of these into every car we build, or 4 of these into every car we build, it's going to be very costly. So we'd like to reduce the cost of our pressure transducers. That probably means using slower pressure transducers. And in this week's individual assignment, you're going to explore the consequences of using slower transducers in your pressure measurements to see, could you get an adequate pressure measurement with the transducers we used in the lab to follow something that was happening this fast? Could you follow it with your Arduino? Is your Arduino fast enough? And how fast would a pressure transducer have to be in order to follow this transient well enough to give us good engine diagnostics information? So that's the target for this week's assignment. And you'll just be using exactly the same elements of code with a few little modifications to get some information about how it'll behave with different pressure transducers.